We will continue our last topic, that was properties of congruence, that we discussed in last class. Okay, so we discussed some of the results related to congruence, and some of them are related to the multiplication with any integer in any congruence. So uh, let's have two more results related to division in the congruence. The first result states that if AC is congruent to BC modulo M. Okay, so different equations we studied in linear algebra or algebra, that we can divide any integer in any equation, or we can multiply any integer in any equation. But here we have some restrictions in congruence. So if AC is congruent to BC modulo M and the GCD of C and M is 1, then A is congruent to B modulo M. So it means we can cancel this C, or we can divide by C if the GCD of GCD of C and M is 1. Okay, so let's have a proof of this. So suppose AC is congruent to BC modulo M, where, so this is given here, GCD of C and M is equal to 1. Okay, so it's given here GCD of C and M is equal to 1. So we apply the definition of congruence. So according to this definition, if AC is congruent to BC modulo M, it means M divides the difference between AC and BC. So just we are invoking the definition of congruence, and according to that, M divides AC minus BC. Okay, so if M divides AC minus BC, it means that is M divides C times A minus B. Okay, so M is dividing the product C times A minus B. Okay, and we know that the GCD of C and M is 1. So it means M completely divides A and B. For example, if we have a product, for example, if we have a product of 21, okay, and this can be written as 3 times 7. Okay, so or let me take another number, a different number. For example, we have 36, okay, and 36 can be written as 4 times 9. Okay, so if we are saying 3 divides 36, okay, and 36 can be written as a product of 4 and 9. Okay, so if the GCD of 3 and 4 is 1, then 3 divides 9. Okay, 3 divides 9 completely because GCD of 3 and 4 is 9. For example, if we consider a different number, for example, we consider if we consider a number 9 and we say 9 divides 36, okay, and we can write 36 in the product of 6 times 6, okay. Since GCD of 6 and 6 is not 1, okay, so GCD of 9 and 6 is not equal to 1, then 9 does not divide 6, the remaining. Okay? And not necessarily divide actually. Okay? So if GCD of M and C, because this product is completely divisible by M, okay, and there is no role of C in the division, okay, because GCD of M and C is 1, so it means M completely divides A minus B, since GCD of C and M is equal to 1. Okay, so if M divides A minus B, so this implies A is congruent to B modulo M. Okay, so it means if we have products here and here, so we can divide any integer in the congruence if that integer has a GCD equals to 1 with M. Okay. So our next result is the generalization of this result. Okay. For example, if we have we don't have any number which has a GCD equals to 1 with M. Okay. For example, if the GCD is greater than 1, then we have another result which is called the generalization of the previous result. So if AC is congruent to BC modulo M and GCD of C and M is not equal to 1, so this is D, okay. But this case is valid for 1 as well. So it means that's why it's called the generalization. Then A is congruent to B modulo. So in that case, we divide whole equation by C, okay. But we write here modulo M divided by D. So this M must be divided by D or GCD. So that's the result. Okay. Now come to the proof of this result. Suppose AC is congruent to BC modulo M. So that's given here, where GCD of C and M is equal to D. Then by using the definition of congruence, we write M divides AC minus BC, and this implies M divides C times A minus B. Okay. Since the GCD of C and M is not equal to 1, so we can't say that M completely divides C minus B. Okay. So if M completely divides AC minus BC, okay, so it means M is equal to thus, if M is completely M completely divides AC minus BC, so this AC minus BC can be written as any integer times M. Okay, where K is any integer. Okay, where K is any integer. Now this can be written as C times A minus B is equal to Km. Okay, we divide both sides by the GCD D. So we divide by D here at the left hand side. So C divided by D, A minus B equals K times M divided by D. Okay. So we know that the GCD of C and M is D. Okay. So it means D is the greatest number that divides both C and M. So if we divide C by D and M by D, and then we take the GCD of both, so that must be 1. Because the the greatest common divisor of C and M is D. So if we divide both of them by D, then the greatest divisor of C by D and M by D will be 1 only. Okay. For example, let me give an example. Um, for example, we have 12 and 9. Okay. So GCD of 12 and 9 is 3. Okay. So that's the greatest common divisor that divides both 12 and 9. So if we divide 12 and 9 both by 3, so we will have 4 here, and then we will have 3 here. And now the GCD of 4 and 3 is 1. Okay. So it means the GCD of C and D and C by D and M by D is 1. And if we write this in a congruent form, okay, so we can write here M divides M by D divides A minus B. M by D divides A minus B because M by D times an integer is equal to C by D times A minus B. And the GCD of C by D and M by D is 1. So M by D divides A minus B. Okay. So now here we apply the definition of congruence. So according to the definition, A congruent to B modulo M by D. So that's the required result. Okay, now so these are the properties of the congruence. So now we can move to the linear congruences. So okay, so before going to the linear congruence, let me define the congruence or congruence equations. Like for example, we can write AX congruent to B modulo M. So this is a congruence, okay, and this one is called a linear congruence. We can solve this equation, okay, and find the roots of x or the values of x. Similarly, we have ax squared plus bx plus c is congruent to 0 modulo m. So this is quadratic congruence. Okay. So we will solve quadratic congruence later in the next chapter. Okay. So in this chapter we will discuss linear congruences. So all linear congruences are in this form. Okay. You will see linear congruences of that form here. So there is a relationship between linear congruences and linear Diophantine equations that you have already studied in the previous chapter or in first lecture. Okay, so linear Diophantine equation is AX congruent to B modulo M, while this is linear congruence, and linear Diophantine equation is AX plus BY is equal to C. Okay, so this equation has already been studied in the first lecture. Okay, so we will discuss the relation between linear congruence and Diophantine equations. Sometimes the solution of linear congruence is easier than the solution of linear Diophantine equation. So usually we convert linear Diophantine equations into linear congruences. Okay, or sometimes we convert linear congruence into linear Diophantine equation. So here we will see the procedure that how to convert a linear Diophantine equation into linear congruence and linear congruence into linear Diophantine equation. Okay, it's look quite strange that linear Diophantine equation has two variables x and y, while the linear congruence has only one variable x. Okay, but they are equivalent. So here we will see that how can we convert a linear congruence into the linear Diophantine equation. Okay, so let's take the let ax congruent to b modulo m be a linear congruence. Okay, so we assume that this one is a linear congruence. Okay, so we just apply the definition of linear congruence. So by definition, we can write ax minus b is equal to m times some integers. So we as any integer. So we assume y is an integer. So for any integer y. Okay. So now this can be written as ax minus my equals b. So this is linear Diophantine equation. Okay, and we know that if you look at the linear Diophantine equation, ax plus by equals c. Okay, so this linear Diophantine equation is solvable only if the GCD of a and b divides c. Okay, so that's okay. So it means we know that every congruence, linear congruence, can be converted into linear Diophantine equation, and not every linear Diophantine equation is solvable. So there is a condition. So it means when we convert linear Diophantine equation into a linear congruence, so it means not every linear congruence is solvable. So there is a condition to solve a linear congruence as well, and that condition applies in the linear congruence as well. So A remains same. The role of C in the linear Diophantine equation uh, here, okay, so C is actually M in the linear congruence. Okay, sorry, C is B actually in linear congruence. Okay, and B is the coefficient of y. So coefficient of y is m here. So this is B. So this is B in linear congruence, and this is C in linear congruence. Okay. So it means the condition to solve linear congruence is that the GCD of A and M must divides B. Okay. So linear congruence is solvable if and only if A GCD of A and M divides C. Okay, so that's the condition to solve a linear congruence. For example, look at the linear congruence 8x congruent to 10 modulo 6. Okay, so GCD of 8 and 6 is 2. Okay, and 2 divides 10. So it means this equation is solvable. Okay. Sometimes we have equations like 8x congruent to 15 modulo 6. Okay. So the GCD of 8 and 6 is 2, which does not divide 15. So this congruence is not solvable. This linear congruence is not solvable. Okay. So the procedure to solve a linear congruence. How to solve a linear congruence? The procedure is very simple. Or for example, we have a linear congruence 12x congruent to 48 modulo 18. Okay. Okay. First, we will see that whether this linear congruence is solvable or not. Okay. So GCD of 12 and 18 is 6, which divides 48. So it means this, okay, this equation, this linear congruence is solvable. Okay. So before the solution, or before going to the solution of this congruence, we know that every element or every term can be divided by 16. Can be divided by 6. So we can divide every element by 6. So this is 2x congruent to 48, or let me define the procedure. Okay, let me define the procedure first. GCD of 12 and 18 is 6. So this is 6. You can. So if we apply the theorem that we studied before, the second theorem, okay, this one. So if we have a product of two integers here and product of two integers here, and that product has a common factor, then we can divide by that integer. But in that case, we have to divide m by the GCD C. So similarly, if you look at here in the linear congruence 12 and 48. Okay, so 12 and 48. Okay, so the common factor is 12 in okay, at both sides. So in that case, we have to divide this 18 by the GCD of 12 and 18. So the GCD of 12 and 18 is 6. So it means we can divide a common factor, or it's better to write 12 times x congruent to 12 times 4 modulo 18. So this is common factor 12 here. Okay. Okay, common factor, we have a common factor 12. Someone asked me, can we call it a linear congruence equation? So sometimes we can call, but usually we call it a linear congruence only. Okay. Okay. So 12 is a common factor both the sides, so we can divide whole equation, whole congruence by 12. But in that case, we have to divide this m by the GCD, which is 6. Just like if we write AC congruent to BC modulo m, and GCD of A and M is equal to D, then A congruent to B modulo M divided by D. So we divide, the common factor is 12 here, so we divide it by 12. But in that case, we have to write 18 divided by 6. So X is congruent to 4 modulo 18 by 6 is 18 by 6 is 3. So X is congruent to 4 modulo 3. So because we are in the modulo 3, so X is congruent to 1 modulo 3. Because 4 is greater than 3, so we can write 1 as the remainder. Okay. So this linear congruence can be transformed into the equation. It is the simplest form. So according to the definition, if we apply the definition of congruence, we can write x minus 1 is equal to 3 times some integer, or x is equal to 1 plus 3 times some integer t. Okay, so that's the desired solution. X is equal to 1 plus 3t, where 3, okay, uh, okay, so we have a result. The linear congruence AX is congruent to B modulo M is solvable if and only if D divides D, where D is the GCD, where D is equal to GCD of A and M. Okay. So we just solved that the above linear congruence, and we have seen that the GCD of A and M divide B. So this linear congruence is solvable if and only if D is congruent to B. D divides B, where D is the GCD of M. So this is A and M. So this result is equivalent to the result that we studied for linear Diophantine equations. Okay, but here the next part of the result is very important, and this is related to our linear congruence as well. Okay, so if the first part can be converted into linear Diophantine equations as well. So for the second part of the result is, if D divides B, then it has D incongruent solutions. So For congruence, this part is very important. Okay, but first part is same as the as we discussed in the linear Diophantine equations. Okay, so the first part is similar to that, but the second part is very important here. If D divides B, then it has D incongruent solutions. So incongruent means different solutions. So we get D different solutions where D is the GCD, and the corollary is if D is equal to 1 means if GCD of A and M is equal to 1, then AX congruent to B modulo M has a unique solution. Okay, so that is the unique solution. Okay, and this condition is valid for if and only if. So if and only if. So it's better to write here if and only if. Okay, so look at the example that we discussed here. So it has D is equal to 6. Okay, so D is equal to 6. So it means it has 6 incongruent solutions. Okay, so what are those incongruent solutions? Okay, so we take values of T from, or we take any 6 values, 6 consecutive values. So we take values from 0 to 0 to no we can't take 6 here. Okay, so it's better to write 0 to 6. 6 is not included here. So when we put 0 here, so x is equal to 1. When we put x is equal, t is equal to 1, so 4, then 7, then 10, then 13, then 16. Okay, so we put values of t from 0 to 0 to uh, 0 to 5. So we get 6 incongruent solutions. Okay, so these are some limitations. Okay, let's have the example that we discussed in linear Diophantine equations already. Okay, the example was 63x minus 23y equals -7. So that example has already been solved by using the technique of linear Diophantine equations, in which we use uh, Euclidean algorithm. Okay, so here we will solve this linear Diophantine equations, okay, by using linear congruence. So first we need to convert that linear congruence, linear Diophantine equation into the linear congruence. Okay, so this linear Diophantine equation can be converted into two linear congruences. So first we can write 63x. Okay, we know that this part, the coefficient of y is always m, if we consider x as the variable, so 63x is congruent to -7. So there is no need to write -7, or you can write +7 as well. Anyway, just write -7 modulo 23. Okay. So where GCD of 63 and 23 is 1, which divides -7. So it means this linear congruence is solvable. Okay. And the other one, if we consider y as the variable, so if we consider y as the variable, so this will become ax, or you can write -23y is congruent to, in that case, the coefficient of x becomes m, and -7 remains a constant, which is b, so -7 modulo 63. Okay, here we also have the the GCD of 23 and 63 is 1, which divides -7. So this linear congruence is also solvable. Okay, so let's solve the first linear congruence. Okay, 63x congruent to -7 modulo 23. We know that this linear congruence is solvable, and we are looking the solution into the modulo 23. Okay, congruent class. Okay, so this is 63x is congruent to -7 modulo 23. Okay, so 23 multiplied by 3 is 69. Okay, so if we look 63 in the class of 23, so this will be, because this is 69, and 69 is 6 greater than 63, so this is in -6x congruent to -7 modulo 23. Okay, because we are looking solutions in Z23. Okay, Z23 here. So in Z23, this 63 is -6. So we can write -6 here. So -1. Okay, we can divide congruence by negative sign. So 6x congruent to 7 modulo 23. Okay. So in 23, 6 is a, I think you are familiar with the unit. So 6 is a unit, means its inverse is possible. It means you can find a number which can be multiplied with 6 and you will get 1. Okay. So because 6 has an inverse, 6 is a unit in Z23. Okay. And okay, so the inverse of 6 is 4 here. So if we multiply 6x by 4 congruent to, because we have to multiply 4 both the sides, modulo 23. So 4 times 6 is 24, and 24 is 1 in modulo 23. So we can write simply x is congruent to 4 times 7 is 28, and 28 is 5 modulo 23 modulo 23, and so that's the solution. you can write x is equal to 5 plus 23t. Okay. Now, this equation is solvable for y as well. Okay. So you can either solve another linear congruence, or you can put the value of x that we have found from here into the actual linear Diophantine equation to get the value of y in terms of p. Okay. So put in 1. So that's the required value of, and then we put this value in equation 1. So equation 1 implies 63, or alternatively you can solve another linear congruence as well. Okay. So but we are not solving second congruence. Instead of that, we are putting the value of x in equation 1 to get the value of y easily. Okay. So x is 5 plus 23t minus 23y equals negative 7. Okay. So we are not solving this. Okay. I'm writing here. So 63 times 5. 63 times 5. 6 times 60 times 5 is, okay, 300, and 3 times 5 is 15. So this is 315 plus 63 times 23. So 630, 630 plus 630, 12, 1260 is 1260 plus 3 times 63, that's 14. You can use your calculator to get the value of 1449 times t, and then minus 23, y equals negative 7. Now you can bring negative 7 here, negative 23y here, and at the end you will be able to find the value of y, which is 14 plus 63t. Okay. So t is, okay. So t is any arbitrary integer. So now we have this value, y equals 14 plus 63t, and x is equal to 5 plus 23t. Okay. This result agrees with the result that we got earlier uh, when we solved linear Diophantine equation. Okay.